Okay, let's take a look at a few examples of solving equations that involve radicals. Okay, we can start with a simple one. Example 1, the square root of x plus 2 is equal to 5. Now, notice this is an equation where there is a single occurrence of x, and so we solve it in the normal way. We think about what has happened to x to build up this expression. First we've added 2, then we've taken a square root, and we think about the operations that we can apply to undo those two things, but in reverse order. So to undo the taking of a square root, maybe we should square things. So if we square both sides, we see on the right-hand side we just get 25. And on the left-hand side, of course, squaring that will kill off the square root symbol there, and we're left with just x plus 2. Now what we have is just a linear equation. This is straightforward. Subtract 2 from both sides. X equals 23. And we're done, right? Certainly, if I plug 23 in for x, I see that's the square root of 23 plus 2, which is the square root of 25, which is 5. And on the right-hand side, I got 5, so it looks like it works out. Yes, that is indeed my solution. But this little piece where we're checking stuff, that turns out to be very important. Let's see why. Let's look at another example. Very, very similar to the first. Okay, suppose we had the square root of x plus 3 equals negative 2. Now before even doing any work, if you look at it carefully, I bet you can conclude this has no solution. Why? Remember, you're taking the square root of x plus 3. Whatever value you plug in here for x, you're going to take the square root of it. That's a principal square root, which means it has to be a positive value. And negative 2 is not positive. However, suppose you missed that, and you treated it just like this problem. You'd say, well, let's see, we could square both sides. On the right-hand side, of course, we get 4. On the left-hand side, the square root goes away, so we have x plus 3. That's a linear equation, so subtract 3 from both sides, and we get x equals 1. Wait a minute. Why did we get x equals 1 when we know there is no solution? The trick, the thing that's going on here, is when we move from this step to this step. If I were to actually plug 1 back in here, I get the square root of 1 plus 3. That's the square root of 4. That's a 2 equals negative 2. If I plug 1 into this top equation, I end up with a false statement. 2 is not equal to negative 2, but that's what I'm seeing. But the instant I square both sides, now I get 4 equals 4. That is a true statement. Okay? So when you square both sides, you run the risk of producing extraneous solutions, things that work from there on, but don't work in the preceding equations. Now, it's worth pointing out that we're never going to lose any solutions that we should have up here. If this equals that, then this squared definitely equals that squared. And so whatever value of x that solved this equals that will be a solution to this squared equals that squared. But we might pick up additional solutions that really are not solutions, that require a check of that first step to throw them out. Okay, so indeed, the answer here is no solution. Okay, let's take a look at another example. Example 3. The square root of x plus 4 minus 3 equals 0. Okay, this is actually not much more complicated. The point in bringing this example up is that we want to resist the temptation upon seeing this square root to immediately just go ahead and square both sides. That won't result in what we would like to see. Let's go ahead and do it just so that you can see that. If we do this, then we have a binomial here squared, which is the square of the first term, x plus 4, plus twice the product of these two terms. That would be minus 6 times the square root of x plus 4, and then last but not least, plus the last guy squared. Notice by squaring both sides, our square root did not go away. Okay? Instead, let's not do this. Instead, let's isolate the square root on one side. So we just add 3 to both sides here. Now it's all by its lonesome. Now, if you want to square both sides, that square root does indeed go away because you don't have this middle term popping up. So we have x plus 4 equals 9. And then, of course, subtracting 4 from both sides, we get x equals 5. And don't forget, of course, because we squared both sides, we're going to have to check that value back in the original equation. So, is the square root of 5 plus 4 minus 3 what we want to see, namely 0? Sure it is. That's the square root of 9 minus 3, which is 3 minus 3, or 0. So yes, it works. Okay? So again, the moral of the story in this example is isolate the radical before squaring it away. All right, let's look at another one. Example 4. X plus 1 plus the square root of x plus 7 equals 0. Okay, here again, I've got the square root, but it's involved with a sum right now. If I squared both sides, I'd end up with some middle terms that would still have radicals attached to them. So let's isolate this square root. Let's take it to the other side. That'll be negative square root of x plus 7. Now, I suppose there's still a negative attached here, but if I square both sides, does the radical go away? Sure. I get x plus 1 squared on the left. Squaring this is like squaring this and then multiplying by the square of this. Squaring a negative 1 is positive 1. It doesn't do anything. Squaring this, I just get x plus 7. So the radical's gone, and hopefully things are in a nicer form. And sure enough, we can tell probably at this stage we have a quadratic. Because if I expand this out, I'm going to have an x squared term. X squared plus 2x plus 1 equals x plus 7. And we know how to deal with quadratics. Pull everything to one side. X squared. Subtract this x off and we'll have plus x. Subtract this 7 off, we'll have minus 6 equals 0. Once you have that 0 on that one side, we can try to factor. And if it doesn't factor, we can always use the quadratic formula. This one, however, factors. We have an x, we have an x. To make x squared, to make a 6, a 2 and a 3 might be considered. The product has to be negative, so they're different signs. I need to end up with a positive x when I'm done. If I make that a negative and that a positive, that's going to work, right? 3x minus 2x is a single x. Equals 0. And so a product equaling 0 tells us that either this factor is 0 or this factor must be 0. And these are two linear equations, so they're easy to solve. Add 2 to both sides here and subtract 3 from both sides here. Okay? So either x equals 2 or x equals negative 3. But remember, we've got to check. The instant we did this, there's a possibility we have extraneous solutions. The instant we squared both sides. So let's plug into this original equation. 2 plus 1 plus the square root of 2 plus 7. What does that equal? We hope it equals 0. Well, that'd be 3 plus the square root of 9, which is 3, which is 6. That is not 0. X equals 2 goes away. Doesn't work. What about negative 3? Again, plugging it into the original equation. Negative 3 plus 1 plus the square root of negative 3 plus 7. Negative 3 plus 1 is negative 2. Negative 3 plus 7 is 4. Take a square root of that. That's positive 2. And those, of course, sum to give us 0. And so x equals negative 3 is our solution. Okay, and our only solution. Okay, let's do one more. Example number 5. The square root of x plus 2 minus the square root of x minus 2 equals 2. Okay, notice we have two radicals going on this time. Well, maybe we focus just on one of them at a time. If I wanted to get rid of the square root of x plus 2, what if I isolated it by moving that to the other side and then squared both sides? At least this radical would go away, right, upon squaring both sides. However, on the right, we have a binomial squared, which is going to be the first guy squared plus twice the product, so 2 times that and then times 2 again is 4 times that, plus the last guy squared. Of course, that removes the radical here. Here, though, we still have the square root symbol. But that's okay. Look, we've gone from an equation that has 2 square roots in it down to an equation that only has 1. We've made progress. To further simplify this, let's isolate this square root and square both sides. Okay, we might want to clean things up first, though. In the process of isolating it, we could subtract an x off both sides, and they go away. We have a 4 minus a 2. That's just a 2, which, if I subtract from both sides, kills off that one. So now I have 0 equals 4 times the square root of x minus 2. I can divide both sides by 4 if I want. It gets the number smaller. That's always good. 0 divided by 4 is still 0. And now I can finally square both sides. That gets rid of the radical. I have x minus 2 on the right equals 0. This is just linear. Add 2 to both sides. And we have a solution for x, we think. Remember, this act of squaring both sides and this act of squaring both sides, either one might have introduced an extraneous solution. So I have to check. I have to go back up here to the original equation and say, well, what is the square root of 2 plus 2 minus the square root of 2 minus 2? This, of course, is the square root of 4, which is 2. This is the square root of 0, which is 0. And that is indeed 2, which is what I was hoping it to be. So x equals 2 is a solution, and the only solution to that equation. Okay? That's it.